Humanity is trapped, not by technology, not by time, but by the fabric of space itself. Every galaxy you see in the night sky is unreachable, and the universe is making sure it stays that way. And one quick question: if you could travel 1 light year per second, where in the universe would you go first? Comment down below. I will pin the most creative answer. Now let's begin. On a clear, moonless night, away from city lights, you can actually spot a faint smudge in the constellation Andromeda. That little patch of light. It's the Andromeda Galaxy, and it's the farthest thing you can see without a telescope. It looks small and unimpressive, but here's what blows my mind. You're seeing light that has been traveling through space for 2.5 million years. When that light left Andromeda, our human ancestors hadn't even discovered fire yet. They were just beginning to use stone tools. Saber-toothed cats still roamed the Earth. The light you're seeing tonight started its journey long before human civilization even existed. And here's the kicker: Andromeda is our closest major galactic neighbor. It sits approximately 2.5 million light-years away from us. That means if you could somehow travel at the speed of light, which is over 186,000 kilometers per second, it would still take you 2.5 million years to get there. Let that sink in. The speed of light is so fast that it could circle the Earth 7.5 times in a single second. Yet even at that incomprehensible velocity, reaching Andromeda would take millions of years. But wait, there's more to this story that makes it even more fascinating and, honestly, a bit unsettling. Andromeda isn't just sitting there peacefully in space, it's actually moving toward us at about 68 kilometers per second. Now, before you panic, we've got time. Scientists predict that in about 4.5 billion years, our Milky Way and Andromeda will collide and eventually merge into one enormous elliptical galaxy. Some astronomers have already nicknamed this future cosmic entity Milkdromeda or Milkdromeda. By the way, if you're wondering whether humans will be around to witness this spectacular collision, the answer is probably not. Our sun will have become a red giant by then, making Earth uninhabitable long before the galactic merger happens. Now you might be thinking, okay, 2.5 million light-years is incredibly far, but it's just one galaxy. How bad can it really be? Well, buckle up, because Andromeda is actually ridiculously close in cosmic terms. It's practically in our backyard. When we start looking at galaxies beyond our local neighborhood, the distances become so vast that our brains literally aren't equipped to comprehend them. Let me put this in perspective. The Milky Way, Andromeda, and about 50 other smaller galaxies form what astronomers call the local group. This is our cosmic neighborhood, spanning roughly 10 million light-years across. Beyond this, there's an enormous void before we reach the next cluster of galaxies. The Virgo cluster, which contains about 1,500 galaxies, sits approximately 55 million light-years away. That's 22 times farther than Andromeda. The distances just keep getting more absurd from there. The famous Coma cluster, 300 million light-years away. The Hercules cluster, 500 million light-years. And we're still talking about relatively nearby structures in cosmic terms. We haven't even begun to discuss the truly distant galaxies that telescopes like Hubble and James Webb have revealed to us. Speaking of which, in January 2025, the Hubble Space Telescope completed one of its most ambitious projects ever. Over more than a decade, using over 600 overlapping images, Hubble created the largest and most detailed photograph of the Andromeda Galaxy we've ever had. This incredible mosaic captures over 200 million stars in stunning clarity. Looking at that image, you realize that every single point of light represents a sun, potentially with its own planetary system, and the entire galaxy is so far away that its light takes millions of years to reach us. Subscribe to this channel and give it a thumbs up if you're enjoying this journey through the cosmos. Your support helps me continue exploring these incredible mysteries with you. But here's where things get really interesting, and this is something that doesn't get talked about enough. The distances we're discussing aren't actually fixed. They're changing, and not just because galaxies are moving through space, like Andromeda is moving toward us. The space itself between galaxies is stretching. This is where we need to talk about cosmic expansion, and trust me, this is going to make the distances seem even more hopeless than you already thought. In 1929, astronomer Edwin Hubble made one of the most groundbreaking discoveries in the history of science. Actually, let me back up for a second, because Edwin Hubble's story itself is pretty remarkable. Before 1925, most astronomers believed that the Milky Way was the entire universe. They thought those fuzzy spiral nebulae they could see through telescopes were just clouds of gas within our own galaxy. Hubble proved them spectacularly wrong. Using the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble identified individual stars in what we now know as the Andromeda Galaxy. By measuring these stars, he determined that Andromeda was far too distant to be part of the Milky Way. Overnight, our understanding of the universe expanded infinitely. We went from thinking we lived in a single galaxy universe to realizing we occupied just one galaxy among countless others. But Hubble didn't stop there. By studying the light from distant galaxies, he noticed something peculiar. The light from nearly every galaxy was shifted toward the red end of the spectrum. This redshift, as it's called, indicated that galaxies were moving away from us. And here's the truly mind-blowing part. The farther away a galaxy was, the faster it appeared to be receding. This led to what we now call Hubble's law, which states that the velocity at which a galaxy moves away from us is proportional to its distance. This wasn't just galaxies randomly moving apart through space. This was evidence that space itself was expanding, carrying galaxies along with it like raisins in rising bread dough. Now, you might be wondering exactly what this expansion means. Imagine you're an ant standing on the surface of a balloon that someone is inflating. From your perspective, all the other ants on the balloon are moving away from you. But here's the thing, none of the ants are actually walking. The surface they're standing on is stretching. That's what's happening with galaxies and space. The rate at which space expands is called the Hubble constant, and measuring it precisely has become one of the most important and controversial problems in modern cosmology. As of April 2026, the most precise measurement we have comes from the H0 Distance Network collaboration. They reported a value of 73.5 kilometers per second per megaparsec, with an uncertainty of just over 1%. That's an incredibly precise measurement. But what does that number actually mean? Let me break it down. A megaparsec is roughly 3.3 million light years. So what this tells us is that for every 3.3 million light years of distance between us and a galaxy, that galaxy appears to be receding from us about 73.5 kilometers faster per second. A galaxy that's 6.6 million light years away is receding at roughly 147 kilometers per second. A galaxy that's 33 million light years away is moving away at about 735 kilometers per second. And this is where things get really wild. The farther away a galaxy is, the faster it's receding. Eventually, we reach a distance where galaxies are receding from us faster than the speed of light. Now wait, didn't I just say that nothing can move faster than light? That's still true. The galaxies themselves aren't moving through space faster than light. Space itself is expanding so rapidly at extreme distances that the cumulative effect carries galaxies away from us at superluminal speeds. This creates something called the cosmic horizon, or the edge of the observable universe. Beyond a certain distance, space is expanding so quickly that light from those regions will never, ever reach us. It's not that those regions don't exist. They're just forever beyond our ability to observe. no matter how long we wait or how powerful our telescopes become. So how big is this observable universe bubble we're trapped in? The current estimate is that the observable universe is approximately 93 billion light-years in diameter. Now you might be thinking, wait a minute, if the universe is only 13.8 billion years old, shouldn't we only be able to see 13.8 billion light-years in any direction? That's a really smart question, and it highlights exactly why cosmic expansion is so mind-bending. You're right that the universe is 13.8 billion years old, and light has been traveling for 13.8 billion years. But remember, space has been expanding this entire time. Objects that emitted light 13.8 billion years ago weren't just sitting still. As their light traveled toward us, space continued to stretch, carrying those objects even farther away. So while the light we're receiving started its journey 13.8 billion years ago, the objects that emitted it are now much, much farther than 13.8 billion light-years away. They're now roughly 46.5 billion light-years away in any direction, giving us that 93 billion light-year diameter for the observable universe. By the way, if you're curious about just how long it would take to cross our own galaxy at various speeds, including the speed of light, I made a detailed video called "How Long Would It Really Take to Cross Our Galaxy?" that explores exactly that question. You can check it out after this one. It really puts galactic distances in perspective before we even start talking about the spaces between galaxies. Now let's talk about the most distant galaxies we've actually observed. The James Webb Space Telescope, which launched in December 2021 and became fully operational in 2022, has revolutionized our ability to see the earliest and most distant galaxies in the universe. In May 2024, astronomers using Webb discovered a galaxy designated Jade's GS. This galaxy was observed as it existed just 290 million years after the Big Bang, when the universe was only 2% of its current age. Think about that for a moment. We're looking at a galaxy that formed when the universe itself was still in its cosmic infancy. The light we're detecting from this galaxy has been traveling through space for over 13.5 billion years. That's longer than our sun has existed. That's longer than our solar system has existed. That light began its journey long before Earth formed, long before life emerged anywhere in our cosmic neighborhood. But here's what makes Jade's GS so fascinating and puzzling to astronomers. This galaxy is bizarrely large and luminous for something that formed so early in the universe's history. The galaxy measures more than 1,600 light-years across and contains several 100 million times the mass of our Sun in stars. Astronomers Stefano Carniani and Kevin Heinlein, who helped discover this galaxy, posed a crucial question. How can nature make such a bright, massive, and large galaxy in less than 300 million years? This discovery challenges our understanding of how galaxies form and evolve. According to our models, galaxies should start small and gradually grow over billions of years through mergers with other galaxies and by pulling in surrounding gas to form new stars. But JD's GS appears to have grown massive remarkably quickly, suggesting that the early universe might have been far more dynamic and efficient at galaxy formation than we previously thought. The light from this distant galaxy has experienced what astronomers call redshift. As space expands, it stretches the wavelengths of light traveling through it, shifting visible light toward the red end of the spectrum and eventually into infrared wavelengths. JD's GS has a redshift of about 14, meaning the wavelength of its light has been stretched to 14 times its original length. This is why the James Webb Space Telescope, with its powerful infrared instruments, is so crucial for observing these distant objects. By the time light from the earliest galaxies reaches us, it's been shifted so far into the infrared that visible light telescopes like Hubble can barely detect it, if at all. Now let's put all of this together to understand just how isolated we really are. Our nearest major galactic neighbor, Andromeda, is 2.5 million light-years away. That's our closest companion in a universe containing hundreds of billions of galaxies. The local group of galaxies that includes us spans about 10 million light-years. Beyond that, there's relatively empty space until you reach the next major cluster of galaxies tens of millions of light-years away. And all of this exists within an observable universe that's 93 billion light-years across, but which is just a bubble of what we can see. The actual universe likely extends far beyond that, perhaps infinitely, filled with galaxies we will never observe because space between us and them is expanding too rapidly for their light to ever reach us. Here's another way to think about these distances. Even within our own solar system, the speed of light creates significant communication delays. When we send commands to the Mars rovers, like Curiosity or Perseverance, there's a delay between 3 and 22 minutes one way, depending on where Mars is in its orbit relative to Earth. At its closest, Mars is about 54.6 million kilometers away, and light takes about 3 minutes to travel that distance. At its farthest, Mars is roughly 401 million kilometers away, and the light travel time stretches to over 22 minutes. Think about what that means for controlling a rover. If an engineer on Earth sees the rover approaching a dangerous cliff through the camera feed, that image is already at least 3 minutes old. If they send a stop command immediately, it takes another 3 to 22 minutes to reach the rover. By the time the rover receives and executes the command, 6 to 44 minutes have passed since the dangerous situation was first observed. This is why Mars rovers need sophisticated autonomous navigation systems. They simply can't wait for human guidance for every decision. Now scale that up to interstellar distances. Light from Proxima Centauri, the nearest star to our Sun, at 4.24 light-years away, takes 4.24 years to reach us. If we sent a signal to a hypothetical probe orbiting Proxima Centauri, we'd wait 4.24 years for our message to arrive and another 4.24 years for any response. That's an 8.5-year round-trip communication delay to the nearest star beyond our Sun. And remember, Proxima Centauri is our closest stellar neighbor. Most stars in our galaxy are thousands or tens of thousands of light-years away. The Milky Way itself is roughly 100,000 light-years in diameter. If you could send a message from one edge of our galaxy to the other at the speed of light, it would take 100,000 years to arrive. But we're not talking about distances within our galaxy, we're talking about the distances between galaxies, and this is where the isolation becomes truly profound. Let's revisit Andromeda, sitting 2.5 million light-years away. If an alien civilization in Andromeda pointed a powerful telescope at Earth right now, they wouldn't see us. They wouldn't see modern humans, agriculture, or civilization. They'd see Earth as it was 2.5 million years ago in the middle of the Pleistocene epoch. They'd see a planet covered in Ice Age glaciers inhabited by our distant ancestors who were just beginning to use primitive stone tools. If those aliens sent us a message today, we wouldn't receive it for 2.5 million years. And if we replied immediately, they wouldn't get our response for another 2.5 million years. That's a 5 million year conversation lag for our nearest major galactic neighbor. This creates what I think is one of the most lonely and humbling realizations in all of science. Any potential alien civilization we might observe in another galaxy, we're seeing as they were millions or billions of years ago. They might not even exist anymore. Their entire civilization could have risen and fallen, and we wouldn't know for millions of years. Similarly, if aliens in distant galaxies are looking at us right now, they're seeing Earth's distant past. We are, in a very real sense, alone in the present moment. Every galaxy we observe exists in our past. Every galaxy that could potentially observe us sees our past. Now let's talk about something that makes this isolation even more severe: cosmic voids. The universe isn't uniformly filled with galaxies. Instead, galaxies cluster together in groups, then those groups form larger clusters, and those clusters align into enormous filaments and walls that stretch across hundreds of millions of light years. Between these structures lie vast, nearly empty regions of space called voids. One of the most famous of these voids is the Boötes void, sometimes called the Great Nothing. Discovered in 1981 by astronomer Robert Kirshner, the Boötes void is a roughly spherical region centered about 700 million light-years from Earth. With a radius of approximately 62 megaparsecs, or nearly 200 million light-years, it's one of the largest known voids in the observable universe. Here's what makes the Boötes void so striking. In a typical region of space that size, you'd expect to find roughly 2,000 galaxies. The Boötes void contains only about 60. Imagine that, a sphere of space 200 million light-years across that's almost completely empty. The few galaxies that do exist in the Boötes void are clustered in a tube-shaped region running through the center, making the void even emptier than it first appears. Interestingly, we might be living in a void ourselves, though not nearly as extreme as the Boötes void. Some astronomers have proposed that the Milky Way sits within something called the KBC void, also known as the local hole, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who studied it in 2013. This proposed void would be roughly 2 billion light-years in diameter, making it 7 times larger than the typical void. The existence of the KBC void is still debated among astronomers, but if it exists, it would mean we're living in a region of space that's significantly less dense than average. This would have profound implications. It might help explain some puzzling observations about the expansion rate of the universe, known as the Hubble tension, where different measurement methods give different results. If we're in an underdense region, the expansion rate we measure locally might differ from the average expansion rate across the whole universe. These voids aren't truly empty, of course. They contain dark matter, dark energy, and a very sparse distribution of gas, and perhaps some dim, isolated galaxies. But in terms of the bright star-forming galaxies we're familiar with, they're remarkably barren. If an alien civilization somehow found itself in the middle of a supervoid like the Boötes void, their night sky would be nearly blank. They'd have to look hundreds of millions of light-years in any direction before encountering significant numbers of galaxies. For them, the universe would seem even more empty and isolated than it does for us. Consider what this cosmic architecture means for galactic isolation. Not only are galaxies separated by millions of light-years, but many galaxies are separated from their nearest neighbors by hundreds of millions of light-years of nearly empty void space. These void galaxies are about as isolated as it's possible to be in our universe, but here's where the story takes an even darker turn, and this is something that doesn't get discussed enough in popular science. The universe isn't just expanding, the expansion is accelerating. And this acceleration is making the isolation between galaxies worse over time. In 1998, 2 independent teams of astronomers made a discovery that shocked the scientific community and ultimately earned them the Nobel Prize. They were studying distant supernovae, using them as cosmic distance markers, and they expected to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The universe's expansion was speeding up. This discovery revealed the existence of dark energy, a mysterious force that makes up roughly 68% of all the energy in the universe. We don't know what dark energy is, we don't know where it comes from, we don't even know if it's truly a form of energy in the conventional sense. What we do know is that it's causing space itself to expand at an accelerating rate, and this has profound implications for the long-term future of the universe and our cosmic isolation. Recent findings have made this picture even more intriguing and unsettling. In March 2025, the Dark Energy Spectroscopic Instrument, or DESI, which operates at the Kitt Peak National Observatory in Arizona, announced results that challenge our understanding of dark energy. DESI created the largest three-dimensional map of the universe to date, tracking millions of galaxies across billions of years of cosmic history. Their data suggests that dark energy might not be constant. It might be changing over time, potentially weakening over the past 4.5 billion years. This discovery was bolstered in March 2026, when DESI released an analysis of more than twice as much data, pointing even more strongly to the same conclusion. A second independent group, the Dark Energy Survey, or DES, reported similar findings, creating a growing scientific consensus that something strange is happening with dark energy. Now, why does this matter for galactic isolation? If dark energy is indeed changing, it affects predictions about the ultimate fate of the universe. For decades, cosmologists have assumed that if dark energy remains constant, the universe will continue expanding forever, eventually resulting in what's called the heat death, or big freeze. In this scenario, galaxies accelerate away from each other, stars eventually burn out, matter decays, black holes evaporate, and the universe becomes a cold, dark, empty expanse with nothing but a few stray particles drifting through infinite space. But if dark energy is weakening, other possibilities emerge. Some models suggest that if dark energy weakens enough or even reverses, gravity could eventually overcome the expansion, pulling all galaxies back together in what's called a big crunch. The universe would collapse back into a singularity, perhaps to begin again in another Big Bang. However, based on current observations, even if dark energy is weakening, it's still driving accelerated expansion right now. And that means the isolation between galaxies is getting worse with every passing moment. Here's what that acceleration means in practical terms. There's something called the cosmic event horizon, which is different from the particle horizon we talked about earlier. The particle horizon defines what we can currently observe based on the age of the universe and the speed of light. The event horizon defines what we will ever be able to observe, even if we wait forever. Because of accelerating expansion, there are galaxies we can see right now whose light will never reach us in the future. These galaxies are receding from us so quickly that any light they emit from this moment forward will never catch up to us. The space between us and them is expanding faster than light can cross it. In fact, cosmologist Abraham Loeb from Harvard University calculated that if the universe continues its accelerated expansion, images of distant galaxies will eventually become frozen in time from our perspective. As these galaxies accelerate away and cross our event horizon, the last photons from them will become increasingly redshifted, stretched to longer and longer wavelengths until they fade into invisibility. But the image won't simply disappear. Instead, it will freeze, showing the galaxy as it appeared at a particular moment in its history, and that frozen image will gradually become dimmer and redder until it fades from view entirely. This means that if we observe a galaxy at redshift 5 or 10 right now, we might only ever see it up to an age of about 4 to 6 billion years. We'll never see what that galaxy looks like when it reaches the current age of our universe, 13.8 billion years. The galaxy will remain forever young in our observations, frozen at an earlier stage of its evolution, because the light showing its later stages will never reach us. Even more unsettling, this process is already underway. Galaxies at extreme distances are already crossing our event horizon. Every second, thousands of galaxies are slipping beyond the point where we can ever receive signals from them again. The observable universe is shrinking in terms of what we'll be able to see in the future, even though the total universe continues to expand. Now think about what this means on the timescale of billions or trillions of years. Currently, we can observe galaxies throughout a sphere roughly 93 billion light-years in diameter. But in the distant future, if accelerated expansion continues, that observable sphere will shrink. Galaxies beyond our local group will fade from view, becoming invisible no matter how powerful our telescopes become. Eventually, in perhaps 100 billion years or so, an astronomer looking at the night sky from Earth, assuming Earth still exists, would see only the galaxies in our immediate local group. Everything else would have accelerated beyond the cosmic horizon. That future astronomer would look at a sky filled mostly with darkness, with only a handful of nearby galaxies visible. They would have no evidence that billions of other galaxies ever existed. They couldn't discover the Big Bang or cosmic expansion because the evidence would be gone, hidden beyond the horizon. Let me paint a picture of what the distant future might look like. Imagine astronomers trillions of years from now. If any intelligent life still exists, they would live in a universe completely different from ours. When they look up at the night sky, they would see only the galaxies in their local gravitationally bound group. Everything else would have disappeared beyond the cosmic horizon. If they tried to study cosmology, they would find no evidence of the Big Bang, no cosmic microwave background radiation, no distant galaxies showing redshift. They might conclude that their small island of galaxies is all that exists, floating in an infinite, empty void. This raises a profound and slightly disturbing question. Are we in a similar situation right now? Is there evidence of earlier cosmic epochs that has already been erased by expansion, things we can never know about because the information has disappeared beyond our horizon? This is one of those questions that keeps cosmologists awake at night. But let's bring this back to a timescale more relevant to our own existence. Before the universe becomes unrecognizably different, something dramatic is going to happen much closer to home. The Milky Way and Andromeda are heading toward each other at approximately 110 kilometers per second. Despite the overall expansion of the universe, these two galaxies are gravitationally bound to each other as part of the local group, and gravity is pulling them together. For decades, astronomers have predicted that the Milky Way and Andromeda will collide in about 4 to 5 billion years. This prediction was based on measurements from the Hubble Space Telescope showing Andromeda's motion through space. However, in June 2025, a new study published in Nature Astronomy threw a fascinating wrench into this prediction. Using updated data from the Gaia Space Telescope, which has been precisely measuring the positions and motions of billions of stars, astronomers discovered that the collision might not be inevitable after all. The new measurements show that the odds of a Milky Way-Andromeda merger within the next 10 billion years are now estimated at about 50-50. As astrophysicist Till Sawala from the University of Helsinki put it, a coin flip is the more accurate description. However, the story evolved further. In April 2026, another team of researchers using even more refined Gaia data and accounting for systematic errors in the measurements reported that the merger probability might actually be as high as 90%, with a median collision time of around 8 billion years. This demonstrates how cutting-edge astronomy works. As our instruments improve and our data becomes more precise, our predictions get refined, sometimes dramatically. What's particularly interesting is why there's so much uncertainty. The collision probability depends heavily on Andromeda's precise sideways motion, its tangential velocity. If Andromeda is moving mostly straight toward us, a collision is nearly inevitable, but if it has enough sideways motion, it might pass by us like two ships in the night, never actually colliding. The difference between these scenarios comes down to measurements of just a few kilometers per second across a distance of 2.5 million light-years. That's an incredibly difficult measurement to make with precision. Additionally, the calculation has to account for the gravitational influence of other nearby massive objects, particularly the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, and M33, also known as the Triangulum Galaxy, the third largest galaxy in the local group. These massive objects exert their own gravitational pull, affecting the orbital dance between the Milky Way and Andromeda. If the merger does happen, it will be a spectacular event, though fortunately or unfortunately, depending on your perspective, no humans will be around to see it. By that time, our Sun will be approaching the end of its life as a main sequence star, swelling into a red giant that will likely engulf or at least sterilize Earth. But let's imagine for a moment that we could witness the collision. Despite the name, galaxy collisions are not like two solid objects smashing together. Galaxies are mostly empty space. The distances between individual stars are so vast that when two galaxies merge, very few stars actually collide with each other. Instead, the gravitational interactions create spectacular tidal tails, streams of stars pulled out of their home galaxies by gravity. From Earth's perspective, assuming the planet somehow survived, the night sky would be transformed. Andromeda, currently a faint smudge of light visible to the naked eye on dark nights, would grow larger and brighter, eventually dominating the sky. During the closest approaches, the two galactic disks would pass through each other, creating shock waves in the gas and triggering massive bursts of star formation. New stars would light up by the millions, creating brilliant blue regions of young stellar clusters. The gravitational chaos would also feed the supermassive black holes at the centers of both galaxies. These black holes, which are currently relatively quiet, would devour enormous amounts of gas and dust, releasing tremendous amounts of energy and creating what astronomers call an active galactic nucleus. For a period of perhaps a few 100 million years, the merged system would shine as brightly as a quasar, one of the most luminous objects in the universe. After several billion years of gravitational interaction, mergers, and restructuring, the end result would be a single, massive elliptical galaxy. Astronomers have already nicknamed this future galaxy Milkdromeda, or sometimes Milkdromeda. It would contain all the stars from both the Milky Way and Andromeda, roughly 600 billion stars in total, arranged not in a graceful spiral pattern, but in a more chaotic, elliptical shape. Our Sun and solar system, assuming they still exist in some form, would likely be flung into a completely different orbit within this new galaxy. We might end up much farther from the galactic center than we are now, or we could be thrown into one of the tidal tails, becoming part of a stellar stream stretching hundreds of thousands of light years into intergalactic space. But here's the key point regarding cosmic isolation. Even after this dramatic merger, Milkdromeda will still be part of the local group, which also includes dozens of smaller dwarf galaxies. This entire collection of galaxies, gravitationally bound together, will remain isolated from the rest of the universe. Research by cosmologists Kentaro Nagamine and Abraham Loeb has shown that if dark energy continues to drive accelerated expansion, within about 30 billion years, the local group will be completely isolated. All galaxies not gravitationally bound to us will have receded beyond our cosmic event horizon. The local group, including Milkdromeda and its satellite dwarf galaxies, will be an island universe, alone in an otherwise empty observable cosmos. This brings us to one of the most profound implications of cosmic isolation. It's not just a physical problem, it's a technological one that directly affects our ability to ever overcome it. Let's imagine that humanity somehow survives for millions of years and develops the technology to build starships. Let's be wildly optimistic and assume we can build spacecraft capable of traveling at a significant fraction of the speed of light. Even with such advanced technology, the distances between galaxies remain insurmountable barriers. Consider what it would take to travel to Andromeda at 10% of the speed of light, which would be an extraordinary achievement far beyond anything we can currently imagine building. At that speed, the journey would take 25 million years. That's longer than the entire evolutionary history from the earliest primates to modern humans. Even at 90% of the speed of light, approaching the absolute cosmic speed limit, the journey would still take nearly 3 million years. No spacecraft we can conceive of could function for that long. No biological crew could survive. No civilization that launched the mission would still exist when it arrived. The message or information sent back would take another 2.5 million years to return, meaning the round-trip communication time would be 5 million years. Civilizations rise and fall in far shorter periods. Some have proposed generation ships as a solution to interstellar distances within our galaxy. These would be massive spacecraft, essentially self-contained worlds where multiple generations would live and die during the journey. The descendants of the original crew, born and raised entirely in space, would be the ones to arrive at the destination. But generation ships face enormous challenges even for trips within our galaxy, and the challenges become absolutely impossible for intergalactic journeys. Research has suggested that a genetically viable population for a multi-generational voyage would need to be at least several hundred people, possibly thousands, to avoid genetic bottlenecks and inbreeding. This population would need a completely closed life support system that could recycle air, water, and nutrients perfectly for hundreds or thousands of years with zero external inputs. Project Hyperion, an initiative by the Initiative for Interstellar Studies, has attempted to design a realistic generation ship for travel to nearby stars within our galaxy. Their designs reveal the staggering complexity involved. The ship would need to be enormous, potentially several kilometers in length, with rotating sections to provide artificial gravity. It would require closed-loop ecosystems, nuclear or fusion reactors that could operate for centuries, massive radiation shielding, and systems redundant enough to survive inevitable breakdowns over such timescales. But even if we could solve all these technical challenges, generation ships face profound social and psychological problems. The people born on such a ship would live their entire lives in a confined artificial environment, never seeing a planetary sky, never breathing unfiltered air. Studies of isolated communities suggest that cultural drift, social conflict, and mission purpose erosion could occur over generations. What happens if a generation born 200 years into a 1,000-year journey decides they no longer want to complete the mission? What if they want to turn back or stop at some intermediate location? These problems are severe for trips to nearby stars that might take hundreds of years. For intergalactic journeys lasting millions of years, they become meaningless because there's simply no way to maintain any kind of continuous human presence over such timescales. Evolution itself would transform the passengers into something unrecognizable as human long before they arrived. Some have suggested using relativistic time dilation as a solution. According to special relativity, time passes more slowly for objects moving at speeds close to the speed of light. If you could accelerate a spacecraft to 99.9% of the speed of light, time would slow down dramatically for the passengers. A journey that takes millions of years from Earth's perspective might seem like only decades or even years to the travelers. The mathematics is elegant. If you could maintain a constant acceleration of 1g, the same as Earth's gravity, you would experience comfortable artificial gravity during the journey. After about 1 year of acceleration, you would approach speeds where time dilation becomes significant. According to the equations of relativistic spaceflight, with continuous 1g acceleration and deceleration, you could reach Andromeda in about 28 years of ship time, even though millions of years would pass on Earth. This sounds like a solution until you consider the energy requirements. To accelerate even a modest spacecraft to such relativistic speeds requires energy on the scale of entire stars. The fuel needed would be many times the mass of the spacecraft itself. Current proposals involving matter-antimatter annihilation, the most efficient energy conversion process known to physics, would still require fuel masses equivalent to a significant fraction of the ship's mass. And there's another problem. At such speeds, even individual atoms in the sparse interstellar medium become deadly. A hydrogen atom, when you're moving at 99% of the speed of light relative to it, impacts with the energy of a high-speed bullet. The cosmic background radiation, normally harmless, gets blue-shifted into lethal gamma rays. You would need shielding so massive that it would dwarf the rest of the spacecraft. But let's say we solve all of these problems through some future technological breakthrough. Let's say we develop antimatter drives, perfect radiation shielding, and can somehow generate the astronomical energies required. We launch a relativistic spacecraft toward Andromeda. The crew experiences perhaps 30 years of travel time and arrives successfully. Now they're in another galaxy, millions of years in Earth's future. Earth is gone. Our sun has long since died. Our civilization, our species, everything we knew has been extinct for eons. They can never return. They can send a signal back, but it will take 2.5 million years to arrive, and there will almost certainly be no one left to receive it. They are utterly, completely, permanently isolated from everything they came from, stranded in a galaxy full of alien stars with no connection to home except their own memories and records. This is the tyranny of cosmic distances. Even with technology that borders on magical from our current perspective, the isolation between galaxies remains absolute in any practical sense. And remember, we're talking about Andromeda, our nearest large galactic neighbor. Most galaxies are much, much farther away. The galaxies we can see at the edge of the observable universe are billions of light-years distant. Even traveling at the speed of light itself, which physics tells us is impossible for any massive object, you could never reach them because the expansion of space is carrying them away faster than you could travel. This brings us to another dimension of cosmic isolation, not just physical travel, but communication. Even if we gave up on the idea of physically traveling between galaxies, could we at least send signals? Could we establish some form of communication with a civilization in another galaxy, if such civilizations exist? The answer, unfortunately, is almost as discouraging as the prospects for physical travel. All electromagnetic radiation, whether it's radio waves, visible light, or X-rays, travels at the speed of light. This is a fundamental constant of the universe, approximately 300,000 kilometers per second. It sounds incredibly fast, and by human standards it is. Light can circle Earth 7.5 times in a single second, but on cosmic scales, this speed becomes painfully slow. A radio signal sent to Andromeda would take 2.5 million years to arrive. If an alien civilization there received it and immediately sent a response, we would get their reply 5 million years later. The entire exchange would take longer than the span from the earliest humans to the present day. This creates an absurd situation for any attempt at conversation. Imagine trying to have a dialogue where each exchange takes 5 million years. By the time you received a response to your first message, your civilization might not even exist anymore. Your language would certainly have changed beyond recognition. Your entire culture, technology, and perhaps even your species would have evolved into something completely different. But let's think even more fundamentally about communication limits. Some have wondered whether quantum entanglement might provide a way around the speed of light barrier. Quantum entanglement is a phenomenon where two particles can be linked in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, and he was deeply uncomfortable with it because it seemed to violate the speed of light limit. Modern physics has confirmed that quantum entanglement is real. When you measure an entangled particle, its partner's state is instantly determined, even if that partner is on the other side of the universe. This happens instantaneously, not at the speed of light, but actually with no time delay at all. Doesn't this mean we could use entanglement for faster-than-light communication? The answer is no, and understanding why reveals something profound about the nature of information itself. While the quantum correlation between entangled particles is instantaneous, you cannot use this correlation to transmit information faster than light. This is guaranteed by what's called the no-communication theorem in quantum mechanics. Here's why. When you measure an entangled particle, you get a random result. The entanglement tells you that your partner's measurement will be correlated with yours, but you have no control over what result you'll get. You can't encode a message by choosing what state your particle will be in, because the measurement outcome is fundamentally random. The person on the other end sees their particle in a correlated state, but from their perspective, their measurement outcomes are also random. Only when you compare results, which requires sending information through conventional channels at the speed of light or slower, can you see the correlation. So quantum entanglement, despite its instantaneous nature, cannot be used to send information faster than light. The speed of light remains an absolute barrier for communication, just as it is for travel. This means that all communication with other galaxies is subject to the same tyrannical delays as physical travel. A message to Andromeda, 2.5 million years. A message to a galaxy, 10 billion light-years away. 10 billion years one way, 20 billion years round trip. That's longer than the current age of the universe. But there's an even more fundamental problem with intergalactic communication. The signal strength of any electromagnetic transmission decreases with the square of the distance. If you double the distance, the signal becomes 4 times weaker. If you increase the distance by a factor of 10, the signal becomes 100 times weaker. Over intergalactic distances, this effect is devastating. A powerful radio transmission that might be easily detectable within our galaxy becomes unimaginably faint by the time it reaches another galaxy. To detect such a signal, you would need receiving antennas of enormous size, possibly hundreds of kilometers across, and even then the signal would be barely distinguishable from background noise. Research on interstellar communication, which deals with much shorter distances than intergalactic space, has calculated the optimal frequencies and power levels for sending signals between stars within our galaxy. The work of physicist Michael Hipke and others has shown that even for communication within our galaxy to nearby stars, you need powerful lasers or radio transmitters and large telescopes to focus and receive the signals. The optimal wavelengths are in the ultraviolet to X-ray range for maximizing data rates, but this requires technology at the cutting edge of what's physically possible. For intergalactic distances, the requirements become absurd. To send a detectable signal to another galaxy using current technology would require transmitters with power outputs equivalent to significant fractions of a star's entire energy output, and receiving antennas the size of small planets. And this assumes the signal isn't absorbed or scattered by the intervening matter. Space isn't perfectly empty. Even in the vast voids between galaxies, there are occasional hydrogen atoms, dust particles, and clouds of gas. Over distances of millions or billions of light-years, this sparse matter can significantly attenuate signals, especially at certain frequencies. There's also the cosmic microwave background radiation to contend with. This is the afterglow of the Big Bang, a faint microwave signal that pervades all of space. It's incredibly weak by terrestrial standards, but over intergalactic distances, even this faint background noise can overwhelm weak signals, setting a fundamental limit on communication. Recent theoretical work has even explored the possibility of interstellar quantum communication, using photons that maintain quantum coherence over vast distances. But analysis shows that to achieve quantum communication over even the relatively short distance to Proxima Centauri, our nearest stellar neighbor at just over 4 light-years away, would require telescopes over 100 kilometers in diameter on both ends. For intergalactic quantum communication, the requirements become physically impossible with any conceivable technology. So we've established that both travel and communication between galaxies are essentially impossible. But cosmic isolation has an even deeper, more philosophical dimension that goes beyond mere technological limitations. It's not just that we can't reach other galaxies, it's that the universe is actively erasing evidence of its own history and extent. Let me explain what I mean. Right now, in May 2026, we live in what might be called a golden age of cosmology. When we look at the night sky with our telescopes, we can see deep into space and therefore far back in time. We can observe the cosmic microwave background radiation, the afterglow of the Big Bang itself, which tells us that the universe began approximately 13.8 billion years ago in a hot, dense state. We can see thousands of galaxies at various distances, and by measuring their redshifts, we can determine that the universe is expanding. We can see this expansion is accelerating due to dark energy. We can study the large-scale structure of the universe, the cosmic web of galaxy filaments and voids. In short, we have access to observational evidence that allows us to piece together the history and structure of the cosmos. But this won't always be the case. If dark energy continues to drive accelerated expansion, the universe has something called a cosmic event horizon. This is not the same as the particle horizon that defines the observable universe. The particle horizon is simply how far light has had time to travel since the Big Bang. The event horizon is more fundamental. It's the boundary beyond which events happening now will never be visible to us, no matter how long we wait. As the universe expands at an accelerating rate, this event horizon actually shrinks in co-moving coordinates. Galaxies that are currently beyond a certain distance will recede from us so fast that light they emit now will never reach us. The space between us and them is expanding faster than light can cross it. Over trillions of years, this process will have dramatic effects. Distant galaxies will appear to freeze in time as they approach the event horizon, their light increasingly redshifted, becoming dimmer and dimmer until they fade from view entirely. One by one, all galaxies not gravitationally bound to our local group will disappear beyond this horizon, but it gets worse. The cosmic microwave background radiation, that crucial evidence for the Big Bang, is also being redshifted as the universe expands. As physicist Abraham Loeb has calculated, after a few trillion years, the cosmic microwave background will be redshifted into such long wavelengths and low energies that it will become undetectable, essentially disappearing into the background noise of space. Think about what this means. Imagine astronomers in the far future, trillions of years from now, living on a planet orbiting a star in the merged Milky galaxy. When they look up at the sky, what will they see? They'll see the stars of their own galaxy, Milky, and perhaps a few small satellite dwarf galaxies that are gravitationally bound to it. That's it. The sky will be otherwise completely dark. No distant galaxies, no evidence of cosmic expansion, no cosmic microwave background radiation. No redshift measurements showing that space is stretching. If these future astronomers try to do cosmology with the observational evidence available to them, what conclusions would they reach? They would see a static universe consisting only of their local island of galaxies floating in an infinite void. They would have no evidence that the universe had a beginning, no evidence of the Big Bang, no evidence that there are, or ever were, billions of other galaxies beyond their local group. They would, in essence, be returned to a pre-1920s view of the cosmos, when astronomers thought the Milky Way was the entire universe and didn't know about cosmic expansion or the Big Bang. Except it would be worse, because they would actually be correct, given the evidence available to them. Their observable universe would truly consist only of their local, gravitationally bound structure. This raises a profound question that keeps cosmologists awake at night. Are we in a similar situation right now? Has evidence from earlier cosmic epochs already disappeared beyond our horizon? Are there fundamental aspects of the universe's history and structure that we can never discover because the information has already been erased by expansion? Some cosmologists have speculated that we might already be missing crucial information. For example, we can only observe about 60 e-folds of inflation, the rapid exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. But inflation might have lasted much longer, with earlier phases already erased from our view. There could have been entire previous epochs of cosmic history, perhaps even previous cycles of expansion and contraction, of which no trace remains. This isn't just philosophical navel-gazing. It has real implications for how we understand the cosmos. There may be fundamental questions about the universe that are, in principle, unanswerable because the evidence has been destroyed, not hidden in some hard-to-reach place, but actually erased from existence as far as our observable universe is concerned. The astrophysicist Nemanja Kalopa and colleagues have argued that the current era might be the most opportune time in the entire history of the universe to study cosmology. We're late enough that the cosmic microwave background has cooled enough to be observable with our technology, but we're early enough that distant galaxies haven't yet faded from view. We might be living in a brief cosmic window, perhaps a few tens of billions of years wide, during which the universe reveals its full history and structure to any intelligent observers that arise. Before this window, the universe was too hot and opaque for clear observations. After this window, most evidence will have vanished beyond the horizon, and we happen to exist right in the middle of this window. Some find this coincidence troubling, suggesting we might not fully understand the cosmological principle or our place in cosmic time. Now we arrive at perhaps the most unsettling implication of cosmic isolation, what it means for the search for extraterrestrial intelligence and the future of life itself. You've probably heard of the Fermi paradox, named after physicist Enrico Fermi, who, during a 1950 lunch conversation, asked a simple but profound question: where is everybody? Here's the paradox in its starkest form. The Milky Way galaxy contains somewhere between 100 and 400 billion stars. Many of these stars are billions of years older than our Sun. We now know from exoplanet surveys that planets are common. Most stars have them. A significant fraction of these planets orbit in the habitable zone where liquid water could exist. If even a tiny fraction of these planets develop life, and even a tinier fraction of those develop intelligent technological civilizations, there should be millions of advanced civilizations in our galaxy alone. Some of these civilizations would have arisen billions of years before humanity even existed. Even with slow, conservative interstellar travel using technology we can currently envision, perhaps 10% of the speed of light, a civilization could colonize the entire galaxy in just a few tens of millions of years. That sounds like a long time, but it's nothing compared to the billions of years some civilizations would have had to do it. Thanks to recent exoplanet discoveries, we now have good estimates for the first few terms. Stars form regularly, most have planets, and habitable zone planets are common. Some estimates suggest there could be billions of potentially habitable planets in our galaxy. But the later terms, the probability of life developing, becoming intelligent, developing technology, and surviving long enough to be detectable, remain profound mysteries. And here's where cosmic isolation becomes deeply relevant. One proposed resolution to the Fermi paradox is called the Great Filter. The idea, articulated most clearly by economist Robin Hanson, is that there must be some extremely difficult step or series of steps between dead matter and galaxy-spanning civilizations. This filter reduces the vast number of potential sites for life down to the tiny number we actually observe, currently just one, us. The terrifying question is, where is the great filter? Is it behind us or ahead of us? If the filter is behind us, if the incredibly difficult steps are things like the origin of life itself, or the evolution of complex cells, or the development of intelligence, then we might be extraordinarily lucky to have made it this far. In that case, we might be alone or nearly alone in the galaxy, but our future could be bright. But if the great filter is ahead of us, that's much worse. It would mean that while life and even intelligence might be common, something consistently prevents civilizations from spreading across the galaxy. Perhaps advanced civilizations inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence gone wrong, or technologies we haven't even imagined yet. Perhaps the step from planetary civilization to interstellar civilization is simply too difficult. And here's where cosmic isolation enters the picture in a chilling way. The isolation we've been discussing, the impossibility of intergalactic travel and communication, essentially guarantees that each galaxy is its own isolated island. Even if civilizations arise and spread throughout their home galaxies, they can never reach other galaxies. This means that every galaxy must independently go through whatever the great filter is. There's no possibility of help from neighboring galaxies, no galactic federation spanning the cosmos, no sharing of wisdom or technology across the cosmic voids. Each galaxy is entirely on its own. Some researchers, like Stuart Armstrong and Anders Sandberg, have argued that even intergalactic colonization might theoretically be possible using relativistic spacecraft, and that a sufficiently advanced civilization could spread across the entire observable universe in cosmological timescales. But as we've discussed, the practical barriers are so immense that this remains purely theoretical. The more likely scenario is that galaxies are truly isolated from one another, functioning as separate cosmic experiments in the evolution of intelligence. If intelligent life arises in a galaxy and survives its great filter, it might spread throughout that galaxy, but it will never know if intelligence arose in other galaxies. It will never communicate with them, never share knowledge, never discover if it's truly alone in the universe or just isolated. This isolation has profound implications for the long-term future of intelligence in the universe. No matter how successful a civilization becomes, no matter how much it learns or how far it spreads, it remains forever confined to a single galaxy out of hundreds of billions. The vast majority of the universe's matter, energy, and potential experiences remain forever beyond reach. Recent work by physicists Adam Frank and Woodruff Sullivan has revisited the Drake equation with updated knowledge of exoplanets. They calculated that unless the odds of a civilization developing on a habitable planet are astonishingly low, less than 1 in 10 billion trillion, then humanity is not the first technological civilization the universe has produced. This sounds optimistic, but it actually makes the Fermi paradox worse. If civilizations are or were common, why don't we see any evidence? The silence becomes even more deafening. Perhaps the answer is simply that the isolation we've been discussing is so absolute that civilizations, if they exist, remain invisible to each other. Each galaxy hosts its own story of life and intelligence, evolving in complete isolation, unaware that similar dramas are playing out trillions of kilometers away in galaxies they can see but never reach. Let's step back and consider the ultimate implications of everything we've discussed. The cosmic isolation we've explored isn't just a practical limitation for the present day. It's a fundamental feature of reality that will shape the entire future of intelligence in the universe. If we think on truly cosmological timescales, not just billions but trillions and quadrillions of years, the isolation becomes even more absolute and existentially stark. According to our best understanding of cosmology, the universe will continue expanding forever, driven by dark energy. Over the next few trillion years, star formation will gradually cease as galaxies exhaust their supplies of gas. The last stars will burn out, leaving behind only dead remnants, white dwarfs, neutron stars, and black holes floating through the darkness. Physicist Freeman Dyson famously explored whether life could continue indefinitely in such a universe in his 1979 paper, Time Without End. He proposed that intelligent beings might adapt to progressively lower energy environments, slowing their metabolism and thought processes, but continuing to exist and think for infinite time. However, subsequent work by Fred Adams and Gregory Laughlin in their paper, A Dying Universe, painted a bleaker picture. Even white dwarfs will eventually cool and fade, planets will be ejected from their orbits, galaxies will disperse as stars are flung into intergalactic space. But long before that ultimate heat death, the cosmic isolation we've discussed will become absolute. Within perhaps 100 billion years, all galaxies beyond our local group will have receded beyond the cosmic event horizon, disappearing from view forever. Each surviving galaxy cluster will become its own isolated island universe, cut off from all others, unable to communicate or interact in any way. Any civilization that survives into this era will find itself in a cosmos that has shrunk dramatically. Where we can currently observe hundreds of billions of galaxies, they will see only the handful of galaxies in their local, gravitationally bound group. The rest of the universe will simply no longer exist for them, not just practically but in principle. No signal, no influence, no causal connection of any kind will be possible. This is cosmic loneliness in its most profound form. Not just that we can't easily travel to other galaxies, but that eventually the universe itself will make such travel impossible as a matter of physical law. Each pocket of civilization will be completely alone forever, with no hope of ever encountering another. Moreover, this isolation applies not just to space, but to time. As we discussed earlier, future civilizations will have no access to information about earlier cosmic epochs. The past will be as isolated from them as distant galaxies. They will be stranded in both space and time, unable to see beyond their immediate surroundings, unaware of the vast cosmos that once existed around them. This raises a haunting question about meaning and purpose. If intelligence arises in the universe, struggles to understand its place in the cosmos, develops science and technology, perhaps even spreads across an entire galaxy, what does it all mean if that intelligence is forever isolated, unable to contact or even know about other minds doing the same thing elsewhere? Is the universe full of lonely civilizations, each achieving great things in isolation, never knowing if they're unique or just one of many? Are there countless races of beings asking the same questions we're asking, reaching the same scientific conclusions, experiencing the same cosmic loneliness? Or is the silence we observe telling us something even more sobering, that we might truly be alone? That the great filter lies behind us, and we are the universe's first or only chance to understand itself. These aren't just abstract philosophical musings, they bear on practical questions about the future of humanity and the choices we make now. If cosmic isolation is absolute, if each galaxy is truly its own separate universe with no possibility of contact with others, then the stakes for our survival become even higher. We're not just responsible for preserving human civilization. We might be responsible for preserving the only pocket of consciousness, meaning, and understanding in this entire region of space-time. If we fail, if we succumb to whatever great filter might lie ahead, there might be no one else to pick up where we left off. Our galaxy's chance at intelligence might end with us. This is why the silence of the universe, the Fermi paradox, is so terrifying. It's not just that we don't hear anyone. It's that the cosmic isolation we've explored means we might never hear anyone, and if intelligence is rare enough, we might genuinely be alone in a vast, empty, indifferent universe that will only become more empty and more isolated as time goes on. The universe's cosmic isolation raises profound questions that we've only begun to scratch the surface of. The terrifying silence we observe might have explanations far darker and more complex than simple distance alone. From the great filter to the nature of consciousness itself, from the inevitability of self-destruction to possibilities we haven't even imagined, the reasons for cosmic silence cut to the heart of our existence and our future. If you want to explore the even deeper and more unsettling implications of why the universe remains so hauntingly quiet, check out the video on the screen. In it, we dive into the most chilling hypotheses about what might be filtering out civilizations before they can make themselves known, and what that might mean for humanity's chances of survival. See you there.